Imagine a spaceship, sleek and silver, hurtling through the cosmos. As it approaches the speed of light, something extraordinary happens. To a stationary observer, the spaceship appears to shrink in length. This isn't an optical illusion. It's a fundamental principle of Einstein's theory of relativity known as length contraction. This mind-bending concept challenges our everyday understanding of space and time. It tells us that the length of an object is not absolute, but depends on its relative motion to the observer. The faster an object moves, the shorter it appears in the direction of its motion. Before Einstein, physicists believed that space and time were absolute and unchanging. Then came Einstein's theory of relativity, which revolutionized our understanding of the universe. It proposed that space and time are interwoven into a single fabric called spacetime, and that this fabric is not static, but can be warped and stretched by gravity and motion. Length contraction is one of the bizarre consequences of this flexible spacetime. It arises from the fact that the speed of light is constant for all observers, regardless of their relative motion. This seemingly simple statement has profound implications for the nature of reality. To understand length contraction, we need to shift our perspective. Imagine you are standing on Earth, observing the spaceship as it zooms past at near light speed. From your viewpoint, the spaceship appears to contract in the direction of its motion. The faster it goes, the more it shrinks. However, for an astronaut on board the spaceship, the length of the spacecraft remains the same. This is because the astronaut is at rest relative to the spaceship. Length contraction only occurs for objects moving at relativistic speeds relative to the observer. The speed of light is the ultimate speed limit in the universe. Nothing can travel faster than light, according to Einstein's theory. As an object approaches the speed of light, its length contracts in the direction of motion. If it were to reach the speed of light, its length would theoretically shrink to zero. Of course, no object with mass can actually reach the speed of light, because it would require an infinite amount of energy. However, the concept of length contraction illustrates the profound effects that relativistic speeds have on space and time. Section 5. The Cosmic Ruler. To measure the length of a moving object, we need a ruler that is at rest relative to the object. But what if there is no such ruler? How can we define length in a universe where everything is in motion? Einstein's theory of relativity provides the answer. It tells us that the length of an object is not an intrinsic property but depends on the observer's frame of reference. Length is relative, not absolute. Section 6. A thought experiment, the muon's journey. One of the most compelling pieces of evidence for length contraction comes from the study of cosmic rays. When cosmic rays collide with atoms in the Earth's upper atmosphere, they produce subatomic particles called muons. Muons are very unstable and decay quickly, with a half-life of just a few microseconds. Given their short lifespan, muons created in the upper atmosphere should not have enough time to reach the Earth's surface. However, we observe far more muons at ground level than we would expect. How is this possible? The answer lies in length contraction. From our perspective on Earth, the muons are traveling at near light speed. As a result, the distance between the upper atmosphere and the Earth's surface appears to contract for the muons. This contracted distance allows the muons to reach the ground before they decay. Section 7. Length contraction in action. Length contraction is not just a theoretical curiosity, it has real-world applications. For example, it is an important factor in the design of particle accelerators, which use powerful magnetic fields to accelerate charged particles to near light speed. As the particles approach the speed of light, their length contracts in the direction of motion. This allows them to be squeezed into tighter and tighter beams, increasing the chances of collisions and allowing physicists to study the fundamental building blocks of matter. Section 8. Redefining reality. Length contraction is a mind-bending concept that challenges our intuitive understanding of the universe. It shows us that space and time are not absolute, but are relative to the observer. What we perceive as reality is shaped by our motion and our position in space-time. The implications of Einstein's theory of relativity extend far beyond the realm of physics. It has had a profound impact on our understanding of cosmology, astrophysics, and even philosophy. Section 9. The universe's grand illusion. The universe is full of wonders that defy our everyday experience. Length contraction is just one example of the strange and beautiful phenomena that occur when we explore the cosmos at its extremes. It reminds us that the universe is a far more mysterious and awe-inspiring place than we could have ever imagined. As we continue to probe the depths of space and time, we can expect to uncover even more mind-boggling discoveries that will further revolutionize our understanding of the universe and our place within it.